In the last video, we started an example where we wanted to evaluate both sides of Stokes' theorem for this vector field V over a semisphere of radius A in the upper positive set plane. We computed that the surface integral was equal to minus 2 pi a squared. And in this video, we're going to compute the closed loop line integral at the other side of Stokes' theorem and show that you get the same answer. So you first have to define the path that encloses the surface of your hemisphere. And in this particular case, that path is at the base of the sphere, which is down here. And once again, by the right-hand rule, we're going to go counterclockwise, which will be in the positive direction. Okay, so the curve enclosing our surface is the circle in the z equals 0 plane down there. And because this hemisphere has radius a, that means that our circle also has radius a. So our curve is parametrized as follows. So you have a, so the radius of your circle, cosine u, and I hat, and radius of your circle times sine u. Okay, so the path that we're integrating over is the circle over here. It has radius a, so each one of these points is at a. And because we're integrating over the whole circle, that means that the range for u is from 0 all the way to 2 pi over here. So to calculate our closed loop line integral over this path, we need the derivative of our parametrization with respect to u, and then integrate with respect to our parameter u. And remember, you have to substitute in v your parametrization. So around our path, x is always equal to a cosine of u, and wherever you see a y, you need to substitute it by a sine u, and wherever you see a z, you would put in z is equal to 0 because we're in the z equals to 0 plane. Remember, x now becomes cosine of u, y becomes a sine u, and z is equal to 0, and you take the dot product with this. We can calculate the derivative of our parametrization. This gives us a cosine theta. The derivative of cosine is minus sine. A cos u, the derivative of that is minus a sine u. And the derivative of a sine u is a cos u. And then substituting in our values for y and x, we get, in terms of our parametrization, our new vector field looks like this. And then I'll add the z here in general, but in this case, z is equal to 0 because we're in the z equals to 0 plane. And then taking the dot product of our vector field with this quantity, we get this minus a squared sine squared u minus a squared cosine squared u. And if you factor out a minus a squared, then you can use the identity sine squared plus cos squared is equal to 1. This is just equal to minus a squared. So our closed loop line integral is just minus a squared, which is a constant. We're integrating from u is equal to 0 all the way to u is equal to 2 pi. And we're just left with du because these two simplified. And this is equal to minus 2 pi a squared, which is the same thing we found from calculating the surface integral of the curl of our vector field. Okay. So this shows in this particular example that Stokes' theorem holds, and you can decide for yourself which path you found easier, whether performing the closed loop line integral or doing the surface integral was easier for you. And finally, in the last video, in the next one, we're going to do an example in which we work with conservative vector fields. Specifically, we'll go through how you can find you can reconstruct the scalar field that resulted in a particular gradient field.